So my name is Olivia Quinet. I work as a software architect at Cluepons. And today, the title of my talk is Apply Modern C++ Beyond Type-erasure and Visitor Design Pattern. So first, I should have called it Applied Proxy++. Yes. So the goal is, in fact, to use the type-erasure pattern and at the same time the visitor design pattern. So we would like to create a vector of shape, and we like to access some methods coming from the interface provided by the visitor pattern. So in this case, area and perimeter. But we would also like to draw the shape by applying a visitor to each of the shape that will draw them. So that's the goal. So how can we do that? So the agenda of this talk is, first I will do a very brief summary of what is a software, and we know that it can be compared to always evolving project, a living being, because we need to always accommodate changes, and so it keeps changes and growing. And to be able to accommodate those changes, we would like to have, of course, to implement a flexible architecture for the software so that any change that comes to us, okay, it's fine, I'm ready. My architecture solution can handle those. And so for this, we apply usually design patterns such as the type-erasure and the visitor design patterns. And I will present you a summary of those two design patterns. And for what they are orthogonal, so usually you don't mix them, because they solve one specific part of a problem and the other one solve another part of the problem. So we may have a problem, and we'll show you a possible solution to solve this problem. And then I will follow up with a small demo, and then I will conclude by what I learned. So software is an always evolving project. So that's very crude, but it's to have the idea. So a software, so we take some input, we process them, and we create some outputs. And for this, we use models and abstraction for the input, for all the intermediate state, for the output, and we can represent those models by bytes, by type, by object, and even higher level of abstraction. And the processes are modeled by instruction, function, methods, and so on. And we deal with mistake, with error code and exception, and also good, for example, to put a series of transformation operation into a pipeline where a series of objects are processed. So, in fact, we can say that building a software is like building a factory, but with important points. We have to deal with frequent changes, modification, and upgrades. That's why we need the flexible architecture, and it is to avoid refactoring. Because if we have to do refactoring, it means that the architecture was not flexible enough. And so, more or less, again, this is very simple, but for software, usually we have a first version, alpha, with very little type, small processing, very little action and operation, and then it grows, and the complexity increases, and the number of types of object processing and action increases too. But we have to realize one thing. So for one version, the program, because we are dealing with C++ and everything must be compiled, even we would like to have an architecture that can deal with an open set of type, an open set of operation. For one version, these two sets are finite, they are given. But we like to keep the flexibility to add more if need to. So, hey, sorry. Okay. So in short, what we like to do, so we have for a pipeline, so we have at the beginning the ping rectangle with a fixed set of type and fixed set of action or process operation. And if you want to increase the number of type, we go for the type erasure because it's easy to add additional types. And if you want to add more action, we go for the visitor patterns, and it adds rows, the blue rows. So it's easy too, but it's more difficult in that design pattern to add types. But if you want to go both ways, there is no design pattern to go in that direction. So we need to do some trade-offs, select one or the other one. So, just for recap, this is a brief summary of the visitor design pattern with stud variant and stud visit. So, variant is a template class that can take a series of types. So, V is a variant that can contain an int, a double, or string. So, in the first line, V equals 42, put an integer. In the second line, we put an approximation of pi, and the third line, we put a string, and everything is good. And we can print the content of the variant and get some index too. It's okay. And for the visitor, so studVisit takes a visitor which is callable that I have to accept every possible alternative from every variant defined in the variadic var argument. The potential implementation for this is to have possibly a multi-dimensional table of n function pointers for each specialization of the studVisit, or can also do that with a switch statement. So example. So first one, you can invoke studVisit with lambda, and that lambda will be implemented for all of the potential type of the variant. Second one, it's about the same, except we do some specific operation for some type. So we can specify. And all of the variant must be exhaustive, otherwise we have an error, because otherwise we don't have something defined inside the visit. And we can also use the overload, which is easier way to do this type of thing. So example with the shape. So stud variant of a circle and square. We define two shapes, one a circle, second one a square. And for example, we can visit them with a draw OpenGL visitor. Ah, yes, by the way, if you have questions, do not hesitate to ask them during the talk. I will not mind. So, and I really like the dependency graph introduced by Klaus, so I will print it here. So at the top is what doesn't change a lot, and when you go at the bottom, it's what can change a lot. So we have the circle and the square, which are unrelated classes. We define the shape as a variant of circle and square, and then we have the draw OpenGL capabilities at the bottom. You can do this like this. Okay. So, summary for stud variant. So, the pros. So it's very easy to add an action to a pipeline. You just need to implement all the action for each type of the variant. But of course, there is some cons. Say if you want to add a type to the variant, you have to update all the visitors. And also, for example, stud variant is not well suited if you are going to mix light-weighted object with heavy-weighted object, because you are going to waste a lot of memory, and especially if you have a vector of variant, you may waste a lot of memory. In fact, there was a talk at CPP that was speaking of that, with a vector of variant. So variant might be fine for your implementation, but you have to know the drawback of it. So now the type erasure design pattern. So the goal of this pattern is to provide a value semantic interface, so fixed set of methods, to manipulate unrelated types, so an open set of type that you can add easily to the program without very little modification in the program. So define some shape here, and you can call, for example, the draw method from the interface. It's fine. So behind the scene, so you have the shape, and that shape contains, in fact, a pimple, so a pointer that will contain all the implementation of the interface. It will do the binding. So you have a constructor that creates a pimple, and you have the draw function that will simply call the do-draw of the pimple. So you have the shape const step class or struct that will simply define all the interface. In the shape model, you actually do the binding for the interface for the type. And memory is very easy, very light in a way, but introduce several indirections. So the pimple points to a structure in memory that contains the value that you erased, and a vtable, which is the vtable to the interface for that specific value. So when you go back to dependency graph, at the top you have the shape and the shape concept and shape model. In the middle, again, the unrelated classes, circle and square. And it's when you actually generate a shape class for the circle that you are going to create all the machinery. The compiler creates all the machinery necessary to bind the interface to that specific type, in this case, circle and square. And then you have the OpenGL draw strategy that do not depend on shape, only depends on the circle and square. So the pro and the cons. Pro, easy to add type. Cons, quite difficult to add an action because it requires modifying a lot, adding a lot of code at different places, and so might be heavy. So we know the problem. And so, in fact, the problem is about asking ourselves the question, what's easier, what's more flexible? Is it, if we choose, for example, the stud variant and stud visit, is it easier to add columns? But that means that we will have to recompile a lot of things and might not be practical. Or is it easier to add rows if you are using the type erasure design pattern? Or third option, maybe, it's can we add row in a similar fashion to stud visit? So those are the blue lines at the bottom of the graph. So for the interface, the pipeline does not need to know about the different types of objects. You can add as many things as you want. But for the bottom part, because we are using the visitor design pattern, in fact, the pipeline does need to know the different types of object is going to apply a method to the underlying type that is erased in the type erasure design pattern. And that's, if you think, it's a bit normal because, again, as I said, we need to compile all the options for when we use C++. So we cannot add dynamically a function. We cannot add dynamically type, except if you use dynamic loading libraries. That's something else. And so we need to have all those boxes defined when we run the software. So, and I will show you now a possible implementation of the solution. And so I have two prerequisites. In fact, it's about having a known set of type for a given version of the template. So we do the version 1 of your software. You are going only have to deal with 3 shapes. Maybe in version 2 you have 5 shapes, but they will be known at compile time and run time. So, but you want to be able to end them easily. And so, of course, here I say no dynamic loading of libraries, especially for that, because we don't want to add types at runtime. And it is more a C++ requirement. So the solution must not be intrusive. So I don't want to modify the square or the rectangle or any of those classes. I want to use value semantic. I still want to use the type erasure to add types, having a common interface. And I would like, again, to use the visitor for adding functionalities and operations. So, sorry, I will go through some type erasure boilerplate, but that is something that can be reused for any thing that you are going to use further. So, and it's in fact quite light. You don't have to type everything. Everything is, can be, say, considered as a library. So you have a template base class that will take as a first template argument a concept, then a visitor strategy, and then a pimple strategy. The constructor is easy. Just create a pimple and forwards all the argument to the create pimple. Then you have the move and the copy constructor. And I didn't write it on the slide, but you have something equivalent for the assignment operator. So create the pimple. In fact, again, quite easy. You forward everything to the pimple strategy. And you have to access our pimple to actually play with the pimple in a derived class. So here I present a pimple strategy with the unique pointer strategy, which is often used. So the pimple is a template type, which is simply can be converted to a unique pointer of concept T. Make pimple create the actual model. So we have in the first type name is model, and then all the arguments who actually construct the model. The second function is clone pimple, which will, in fact, very easily call the clone method of the pimple. And the third one makes the copy of the model. And now for the visitor. So we have a visitor strategy, and in fact, simply adding an accept method to the base class that will take a visitor and some arguments, and we transfer everything to the visitor strategy. We have also the const version of the accept method. And so the default visitor strategy, it's very easy. It's just a call operator that called the accept visitor method of the pimple and transfer all of its arguments. So, but with this, we are not far yet. We still need an actual visitor. And so we can define a default visitor, again a template, that will use the curiously recurring template pattern, because we have derived as a first argument. The second template argument is a visitor callable template, so that can be type. And then we have the list of types that the visitor will handle, so the TS. And so, in fact, that visitor, what he will do is will just hold that blue line that I showed you before. So it's all the possible methods of visits for the given type. So we don't need what to do yet, but we know that we are going to be able to call something that needs to match the visitor callable template. So yes, you are telling me that, but maybe no, it's a bit of cheating because you have only one type of visitor. Yes and no, because you can do several default visitor per visitor callable template if you need to. And so how do you initialize? Once you have the visitor methods initialized, you can just forward the call operator, all the arguments of the call operator to these methods, and we'll do a dispatch to the correct method based on the argument. So that operator parenthesis will get, in fact, the underlying type, underlying value in the erased, in the model class. So it's like doing a manual dispatch, but with types. And now it's a bit of machinery to, in fact, initialize this blue vector. So we have a static create function that takes something. It can be a lambda, and it will apply that lambda to each of the types of the methods. And in fact, at that point, it's where the compiler will actually instantiate the lambda with the derived type that it needs to match. So, back to the shape example. So, we declare a visitor structure. We don't define it yet. We declare it. Then we have the shape concept, which will be using a pimple from the pimple strategy we selected, so with shape concept in it. A structure, we define the interface do error and do parameter. And we say we are going to accept a visitor that will take visitor. So the struct we declared before as an argument. We have the clone, and then the model that's going to be defined now. So it's about the same thing. If you follow the talk from close, you will recognize the patterns. So we have everything here. And the clone, it's simply what we call the make pimple clone of the pimple strategy, and everything is hidden for the user. And now we can define shape by deriving from the base class that we saw before, where we pass the shape concept, the visitor strategy, and the pimple strategy. And we define the interface error and parameter by calling the do error and do parameter of the pimple. And that's it. Maybe. We still have to define the visitor, actually. We define the struct visitor that we only declare. We are now defining it later after the shape. And we define it like this, and it takes... so it's derived from the visitor strategy visitor. So we pass again the name of the struct, so visitor. The type of visitor function we are going to use can be a stud function, it can be a function pointer too. If you can, maybe it might be a bit more efficient to use that one. And then you declare all the classes that you are going to use in your pipeline for a given version. So every time you introduce a new shape, you have to modify the visitor. You have to update it. So example, so here we have a shape. So for example, we generate 10 million shape, and we can sum the error by getting the sum over the shape, and we access the error member, the shape at the bottom from the visitor, and then we can draw also all the shape. So the dependency graph is a bit more complex here. But also on the top left, you have the boilerplate. That doesn't change. It will be common for all your type erasure things that you are going to introduce. And for a pipeline, so you define the pimple strategy, the visitor strategy. You declare a visitor, you implement your shape concept and your model, and then do the shape class with everything. So this is at the top. Then we have the circle and square classes that do not depend on anything on the above part. They are very independent. Then you have, in fact, to define the visitor. So we have to list all the, you have to apply it. You have to define all the type of shape you are going to use. And then this one you implement, you instantiate the shape concept model, for example, for the circle that the compiler will make all the link, and also with the visitor. And on the side, you have the OpenGL drawer. So I think with this you have a very, you separate all the concept and all the concern in your program into different parts that are not dependent. The only point of dependence is inside the visitor, because you need to specify at that point, at that stage, all the classes you are going to work with inside the pipeline. So, and I have another implementation, but that's with manual dispatch for the virtual table. It's about the same. So you still have a pimple, and then you have a pointer to VTBL. So instead of one pointer, you have two pointers. But it's about the same. And as maybe where someone will complain or be happy because I did some performance, but here's relative measurement. So the first line is the classic type erasure, all point 1. And the second line is when you use the visitor with a function pointer or student function. I guess the case here I forgot to say. So we are going to measure so the impact of all this machinery by calling the area and perimeter of each shape, so circle, class, and a circle, square, and everything, either via the type erasure interface or via the visitor. The fourth, fifth, and sixth line is about type erasure, but with the manual dispatch. And the last line is with std_variant and std_visit. So you can see that with the classical implementation, we are slower than std_variant, about 10–20% slower. With the manual dispatch, in fact, we are on par, more or less, with the std_variant. And why is that? Well, I think it's more or less because we have we only do one jump in the VTBL. Said we don't need to do, except the classic type erasure, we have to do 2 jumps to go to the VTBL methods. Here we do only 1 jump. So, okay. So, yes, now I will show you a small demo. All the code is available on GitHub if you want. So, yeah. So that's the demo. I don't know if you can read properly, or I should increase. Is it okay for everyone like this? Okay. So here I would like to show you a small demo with animals, because they're cute. And so we, okay. So we would like to create a vector of animals, and we would like to make them sound. So we take all the animals, and we're going to make them sound. Okay. And also we would like to draw the animals with a visitor that can be defined anywhere. So that's the code. I don't know if you have questions about this code or if it's clear. Then the main function, it's very simple. So you create the animal. Here there is only a vector of one animal, which is one sheep. So you call, and you have OpenGL drawer. You create the visitor, and you pass it to your draw animals function. And if you can see, all of those make sounds and draw animals, they don't need to be defined in this compilation unit. They can be defined somewhere else. So you separate everything. And so, for example, okay, so if you compile it, run, of course, there is the expected output, so it's bar for a sheep, and the OpenGL drawer drew a sheep. Of course, it's on the screen. Okay, now. So the animal, so you have the animal concept, so that's the class, the model, then you define the animal. It's like in the slide. So the make sound just called pimple do make sound. But you have to define also the visitor, so yes. And for the moment, it takes only a sheep. And the OpenGL drawer, so of course, it's defined like this, so there is you only accept a sheep for the moment. So now you go to, and that's the sheep class, so it's very easy. Nothing fantastic. So now let's say you want to have, you have a new version of your software and you want to do another animal. So let's say the cow. So whoops.
I have a question.
Yes.
Why is it a friend that is not a public? Why must it be like this?
Oh, it's because I call it into the. We show you why. Yes. So the question is, why do I have a friends make function? It's because I'm calling make sound of animal here in the model class. I can have animal dot make sound, but then it requires animal t to be a class where there is a method called make sound. For example, we have I don't know a string. A string doesn't have a function make sound. But you can define a free function that will accept a string as its first argument. Yeah. And then the compiler will be able to do the link. That's why. Okay, so go back to the cow animal. So cow. Okay. So I need to update this. So the qu'est-ce qu'il m'a fait? So simply add okay. And of course, I have some new animal to draw with the OpenGL. So you have to do this. Yes, and of course, you have to do the implementation. So now I've added a cow to the list of animals. So yes, make. And of course, we have the moo, and we draw the cow with the OpenGL. And so that's with the classic pinball strategy. And now if you want to use the manual dispatch, so it's a bit different. The thing's a bit different because you have now a struct animal VTBL and we have function pointers. So it's about the same, except that we are doing the manual dispatch. And here also, except that here you don't have, you don't need to specify the pinball strategy because in fact everything is managed inside. You don't have to deal with memory management in this thing because the pinball is managed outside the model. It has its own thing for management. So it's completely different, independent. You can do whatever you want. You can do, for example, some small buffer optimization and things like that inside. It's completely transparent from your base class. You just have to specify another pinball strategy. Yeah, and here you have also to do this. So if you have the second one, you have to use co. And again, okay. And now we are going to use the second one. And let's hope everything compiles. Yes, and you have the same result. So in fact, you can change the implementation behind and not change the code that is dependent on it. Of course, we will have to recompile, but there is no change to it. No change for the code that depends on it. Okay. I think I was a bit quick. But, so, I don't know if you have more questions from the demo. Yes?
What happens if you forget to add the... So what happens in your demo if you forget to add the cow type to the visitor? Will it be silently ignored?
No, you will have a lot of problems at the compilation. In fact, let's... Yes, so in fact the question is what happens if we forget to add cow to the visitor? So let's try. And the problem is that because we have templates, you have a lot of errors. But it's with GCC, sorry, it's a bit, yeah. So, and in fact, it says that you cannot call method for the forwarded argument with co because you don't have it. It's when you try to, in the accept visitor function, it's try to call visitor with the co, but he has no option to do it. So he will complain at that stage. Maybe there is a better way with some static assert to do a better message, but I'm not there yet. So yeah. Oh yeah, so. Another question? Oh, okay. Okay, so, comment est-ce qu'on fait encore? So, now I can go to the last part, so what I learned. It's, that was quite an intensive project. I had the impression that I was going somewhere, but it was hard. I talk and exchange of mail with Klaus about it at one point. And yes, it was not easy, and so I had to try and think and retry and think again, but didn't despair. I managed, I think, to find something that works. Says you have to pay some price, and the price that you have to pay is that you have to specify all the types that your visitor is going to be applied on. And so is that price high or is it okay for your project? That's up to you to decide. And yes, so again, there is no free lunch or silver bullet solution. So we cannot, we have always a price to pay, but if you're aware of it, it's fine. And here I think, well, at least for my project, I think I have something that's flexible enough. So I can add any new action, and I can add any new type that I want with quite small price. It's not null, but I think I keep it as low as possible and as acceptable for me. Yes, also, that's a bit simple, but yes, I have to read a lot of language specification, learn new stuff to do this implementation, and I suggest all of you to keep you informed and learn new stuff and try new things, even if it sounds crazy at the beginning. So, thank you. Do you have any question? Any more questions?
Thank you. This is pretty cool. I'm curious, was it something that you were working on because like you were intellectually curious in it, or was there a like concrete problem you were trying to solve, and can you publicly talk about what that motivation was?
Yes. I more or less, I was, yes, when I discovered first the type-erasure pattern, I was like, yeah, great, it's cool. Then I realized, there is some drawbacks. And for me, the main drawback it was hard. For example, to add a function, or for example, in the example that Klaus suggested, you have to put the draw strategy you are going to use inside the shape. And so if you want to change the draw strategy or have different draw strategy at the same time, it's not possible. So it was not it was missing some flexibility. And I say, there might be something to do. And that's come from deep frustration at one point. And yes, there was a lot of code to type and things, and I didn't like it. And I looked at different possibilities around the web, but didn't find exactly what I wanted. So maybe, yes, I reinvented the wheel, but I'm happy with my wheel. So.
We have a couple of questions. We have one question from online. Is this something that you use in production code? Did everything work out of the box, or did you encounter unexpected problems in real-life code?
I just finished it, so it's not yet in production, but it will be, because I think now it's mature enough for me, and maybe I will still have to polish some stuff, because as I still have to add concept for the templates and things like that to do some extra protection. But I have the impression it's working, and so if any of you wants to participate in the project, it's on GitHub, and you're welcome to join. Thank you.
If we still have some time, can you little bit dig deeper in this your own vtable implementation? How did you basically you not using the normal vtable from the class, or you said you are basically doing a dispatch, cutting one level, yes, of dispatching there?
Yes, there is only one dispatch.
And can you little bit more say how did you, what's the difference between normal vtable dispatching, the built-in one and the one that you did?
Oh, okay. So with I would say the classic implementation type-erasure, so you have to go through the people, and then once you have the people, you have to go through the compiler has to go through the VTBL of the virtual tables that is defined for each type. So you do one jump and then the second jump to go to the methods, the implementation of the interface. Here, because I have two pointers, so I have a pinpoint which simply points to the object in memory, and I have a pointer to the VTBL, so I have one, and then I can go directly to the method, so I skip one jump.
Okay, can you show it in your example?
Do you want to see the code?
Yes.
Okay. Well, yes. So this is the struct that will just contain a list of function pointers, and it will be initialized by the call of create. with a specific template, which is called cast-t. I can show it to you later. And that cast-t type is just responsible to cast the void pointer to the actual type. So it's a bit of hidden, but you can do that safely because you master everything in the base class. And so how it is done. So that's the second one.
So you can say it's a little bit like a C solution that you have void and
Yes,
you
yes,
cast
yes.
it to some class by using some metadata, yes?
It's manual dispatch. Yes, it's function pointers, but yeah, and it's everything is encapsulated into classes and structs and hidden. So yeah. But yeah, all the code is available on GitHub. So if you want to read it, and also available for the discussion, because yeah, they
No, it's
can
okay.
go very deep into the detail.
It's okay, it's fine.
Yeah. So yeah. Okay. Another question?
I mean, since we have the time. Hi, thank you for the talk. I'm not sure if I understood one part, which is I can see how you can replace one thing, like let's say, okay, I'm gonna write a DirectX drawer or something,
Uh-huh.
but and I'm not asking you to write it in front of us, obviously, but it's like, what would it involve if I wanted to add another action, another functionality, let's say sing for all the animals or something,
Yes.
or dance?
Yes. Well, you can do that, for example, with the visitor again. And you will have...
I guess I'm wondering how much work would that involve? How many files would I have to touch, or in a general sense?
General sense. I would say one header and one CPP file where you define it. And then, of course, where you are going to call it in the demo. For example, here, you just have to, define this, and then it's okay.
You don't have to change, you just add code.
Yes, just add code. You don't change anything. The only part that you may have to change if, for example, you want a visitor that, the visitor that I use do not return a value, it's a void. But if you want to have a visitor that return a value, then you have to do some changes. You have to add a new type of visitor that returns a double. But that's quite light. So it's not much.
I see. Thank you.
Perhaps I missed that, but when you define visitor,
Yeah.
you use constref types.
Hmm?
You use constref types when you define visitor. I didn't get why you do that as a template argument.
Yes, well, I use. Sorry. I'm.
This is when you added the cow
Yeah.
to the visitor?
Ah, oui, the const. Yes, because the visitor will take a const reference to the cow. That's it. I want to it won't be able to modify the object it's visiting. I don't want to make a copy either.
Ah, okay.
Sorry, I misunderstood your question. Okay, I see. Okay. I don't know if you have any more questions. Otherwise, I'm available later for discussion. And thank you again.